Welcome everyone, and thanks for joining us today. As some of you may know, these tutorials have been designed to provide details about RF components, what they do, how they do it, the related technologies, some of the different configurations, and the myriad of enhancements, design enhancements, and sometimes engineering enhancements that typically have to be made to them so that they can fit customer applications. TRM Microwave is engaged in the custom design and manufacture of a variety of these RF components, hybrids, power dividers, and of course power combiners, which are the subject of today's session. And a power combiner is a relatively small component that fits inside a larger device. And really, it's a very simple thing that it does. It takes power from or signals from two or more ports and directs them into one output port. So maybe it might be used to connect more than one antenna to a single radio, or in some cases to connect multiple radios to a single antenna using the same frequency. Clearly, to do this kind of thing, the power combiner must perform repeatedly and reliably. And again, it will be required to be modified in a number of different ways to fit the customer applications. So to address these variations, I am very happy to introduce TRM's Chief Technology Officer, Shaun Moore, and he will share more of the technical information about the various types of power combiners, the different design configurations, as we've said, and some of the necessary engineering innovations that he and his team have to put into these things. And as some of you may also know, Shaun joined TRM back in the late 90s. He came to the company with a valuable combination of experience and a passion for solving problems, and his skills in these areas have done nothing but grow ever since. So Shaun, maybe I will turn this over to you, and maybe you could start by sharing your objectives for today.
Yeah, thank you, Paul. So today's really what we're going to talk about are power combining and really what differentiates them from power dividers. And really, as far as we're going to start with a little bit of theory, go through a little bit why you'd want to use a power combiner, and then we're going to get into really the nuts and bolts as far as what we're going to go through today, which is really what differentiates them and how do we have to design the part differently to accommodate the power levels of a power combiner. From there, we'll go ahead. We'll talk a little bit about what makes TRM different, and then we'll have a wrap up.
That sounds terrific. Thank you. And you know, whenever people talk about power combiners, they almost always seem to also refer to power dividers. Can you explain why this is so common and maybe define each?
Sure. So basically, a power combiner operates as a backwards power divider. Basically, you take multiple signals and you put them on a single cable. These are used, as you had mentioned in the opening, about taking multiple radios and putting them on a single antenna, or more commonly, using multiple amplifiers to generate higher power levels out on a single antenna. These sorts of applications include using a lot of high power GaN or solid state amplifiers and using them to generate very high levels, becoming very popular for radar applications. For those sorts of applications where we talk about generating very high power levels. Power dividers, on the other hand, take a common signal and distribute up to multiple places. What really makes a power divider different, a power combiner different from a power divider, really has to do with what happens to the energy when you go to do the combining. Power combiners vectorially add or sum the energy. What does that mean? That means that if two vectors or two signals are coming in, same frequency, same phase relationship, they will sum quite nicely and come out the common port of the power divider. What happens when the signals do not correctly align, either because they're coming in with a different frequency or a different phase angle, what happens is that some of that energy adds and some of it subtracts. All the energy that subtracts gets put into the isolation network of the power combiner. So what happens here is that as soon as these signals are no longer completely coherent with each other, or completely aligned, uh, the the isolation circuit absorbs all that energy, and it has to dissipate it as heat. So that's really the big difference between a power divider and a power combiner, is its ability to handle that heat. In a power divider, theoretically, the isolation circuit does very little work. It's a balanced network. Since there's only one signal coming in, of course, we manage the way that that signal gets distributed inside the part, so there's very little power handling in the isolation circuit as part of the network. Power combiners, though, that relationship is really out of our hands, and therefore we have to design these parts to be able to handle very often a worst case scenario of having significant amounts of power being dissipated internal to the device.
Now, does this also incorporate the concept that I've heard discussed a lot when power combiners are being discussed, and people refer to combining efficiency? What does that mean?
Yeah, combining efficiency also has a lot to do with the phase relationship of the signals. Like I said, if you have two amplifiers that are running completely in parallel, they're driving them with a common circuit, so the outputs are exactly coherent. Then it will be very efficient. All that power will be combined and be summed and come out the output. What happens when you do not have that sort of very coherent sort of combining is that you start dropping power. Now, a good example of that is if you have two radios, for example, that are transmitting on different frequencies. The phase relationship is different. What's basically going to happen is that as that energy comes in, since there's no signal on the second input that's going to combine effectively, and that what's going to happen there is that half the energy is going to try to go out the isolated port, and in which case all of that energy is going to be dissipated in the isolation network without having a voltage on the second port that's going to align with the voltage on the first port. That difference of those two signals will go into the isolation network. So basically, if we have non-coherent signals, it has the same split loss as what you would experience in a power divider. So for a two-way power combiner, you'll have 3 dB worth of insertion loss going through the device if you have non-coherent signals. So half of the power that's being put into it will be dissipated in energy in the isolation network.
Okay, that makes sense, certainly. Now, maybe you could talk a little bit, if you would, about the various configurations or different types of power combiners.
Certainly, there are quite a few different ways to do this. Certainly for a power divider, as I spoke about last time, a Wilkinson is a very popular sort of configuration for a standard power divider. It could be used as a power combiner as long as the peak power and the average power that you're putting into that device will not exceed the power handling capability of those isolation resistors. The downfall of a Wilkinson as a power combiner is that the resistors are put in the circuit in a balanced mode. What that means is that there is no electrical or thermal path to ground in order for that to operate effectively and not have a lot of parasitics coming off it, which will impede its performance. Works fantastic because the differential voltages in a Wilkinson network are very minimal, and therefore we don't have to dissipate that much power through that resistor. When you go into a power combiner, on the other hand, we are putting a significant amount of power into a mechanical configuration that is not designed to effectively transmit the heat that's being generated back out to the package. So what do? We go in there and we have different configurations that will allow us to take that isolation network and get an effective heat path down to ground. So what that puts us into are things like ring hybrids, glycerol combiners. Hybrid networks allow us to take that isolation network and bring it out to a nice 50 ohm termination. And radial combiners also do the same thing, where it allows us to take that excess energy and port it out to a nice 50 ohm termination, where we can get a good thermal path down to ground.
Okay, so if I heard you correctly, then there are times when a power divider can be used as a combiner.
Absolutely. If what we're looking for really are a very low power and the thermal considerations are okay, then you sort of can flip the power divider around and use it in that configuration. Once we get up into significant power ranges, though, we really have some issues. And really, the power rating gets significantly derated when we go from a power divider to a power combiner. We just need to keep that in mind. So really, be very careful with those sort of power ratings if we do decide to take a power divider and use it as a power combiner.
Okay. Now I see the term hybrid used here a couple of times. Can you explain a little bit about what hybrids are?
Sure. Are microwave devices that allows us to be able to use them as other power dividers or power combiners in a very good way, because what happens with a hybrid is that there are terminations that are put on here. All the hybrids that we build here at TRM are by nature 4-port devices. We're using either 2 inputs or 2 outputs on this device simultaneously. What happens if we're using this as a combiner is that one port becomes one of the ports becomes the output, and the other port becomes the differential port, or what we would do is we would terminate them. So what happens here is that, and the example that's on the screen right now is for what we call a rat race or a ring hybrid. It's a 4-port device. If we are feeding this device in phase from the 2 outputs, all the energy will be directed to the sum port, and that it'll work very efficiently as a power combiner. The delta port of this hybrid will absorb any excess energy. So, for example, if we have 2 dissimilar signals, half the energy will be directed to the delta port, and then the sum port, the sum of the energy will be directed to the common port. What I will say is, as far as, and this is true of all power combiners, if we have 2 signals of the same frequency but opposite phase, being they're 180 out of phase, all of the energy will be directed to the delta port, and none of it will come out of the sum port. So as we're thinking about these different configurations, this can be a very effective way of taking that excess energy and putting it to a place that can really handle all that power that's coming out to it. Now, what I will say is there are some great things about ring hybrids. There are some fairly significant drawbacks. They're only good for over a fairly narrow bandwidth, typically about a 20%. It's a resonant ring, so therefore its bandwidths are certainly limited by that structure. What I will say also is that we can build this in a number of mechanical configurations. We can build it a microstrip, strip line, or coax to be able to accommodate various frequencies in different mechanical configurations. The good thing about the coax configuration is that we can take the 3/4 wavelength delay line that's part of the structure, and we can actually build that with a ferrite loaded coaxial line, which can give us up to about an octave's worth of bandwidth, significantly improving the bandwidth performance over a straight printed sort of configuration.
Okay, so you mentioned that there are some drawbacks associated with the rat race or the ring hybrids. What other types would you use then in cases where those drawbacks were significant?
Okay, well, as I said, we do have other configurations. Now, the biggest thing here, I think, and the beauty of these 0-180 hybrids is that this is an entire family of parts where the ring hybrid is a subset of. Any 0-180 hybrid can be used as an in-phase power combiner. 0-180 hybrids have 2 output legs, and they have a sum and a delta and a delta output when used as a combiner. Any delta port can be terminated and have this operate as a 2-input power combiner. Whether we're talking about a very broadband printed hybrid like we have on the top illustration, the octave bandwidth hybrid like we have in the middle illustration, and also using a ferrite approach, which is what we have on the bottom. Again, the beauty of even the ferrite approach is that all the energy gets directed to the directed out to the delta port, as opposed to being dissipated in an internal resistor. So here now we're dealing now with the heat limitations of the strip line, the microstrip, or the ferrite devices themselves. And really, with this sort of approach here, we can have the same bandwidths for a power combiner as what we have for a typical 0-180 hybrid. So these can have very broad bandwidths of in some cases we have octave bandwidth. Some places we have the example on the top is the circuit board from a hybrid that we build. It works from 2 to 30 gigahertz. So that's got a 15-to-1 bandwidth, extremely broad bands. So these sorts of configurations can work over very broad bands.
Okay, so let's move back maybe, and can you give us some examples of different types of power combiners themselves?
Sure. Now this is a glycerol combiner. What you see here are some illustrations from Glycerol's original paper. The original this has a similar drawback as the rat ring hybrid, and this is actually a combination of a rat ring hybrid and a Wilkinson power divider. And for the 2-port configuration, which is what we have on the illustration on top, this really works beautifully because it is fully symmetrical. It has 2 50-ohm terminations on it for a 2-port hybrid, which means now that this can handle twice the power of a rat race for a given power output on the termination. These sorts of combiners are used for very high power applications because the more resistors you have in the network, the more you can spread that power around and the higher power you can actually dissipate. The beauty of the glycerol, though, is you can actually start cascading these on top of each other, and you can have as many power combining points really as you need. TRM has built these glycerols up to 10 ways in a radial configuration. So this is actually a very effective way to be able to build this. Now the drawback here, of course, is that again we're down to a 20% bandwidth, but yet we built some very efficient applications with some very good power handling capability over that narrower band.
Okay, and are there other types of combiners that you'd talk about?
Sure. And another one is the non-isolated or radial combiner. This one over here again can be built up at very high power, very low loss. A lot of our commercial customers really like these because the cost is quite competitive, and they're quite efficient. There is a very big downside of this is that there is no isolation circuit in these networks whatsoever. So what happens here is that as long as you're doing in-phase combining and you're combining amplifiers, this does a very effective, beautiful work of acting as a combiner. The downside of this is that once you lose one of your outputs or one of your inputs gets turned off, what happens there is that energy just starts coming back out that would ordinarily be an input, and it can cause significant damage to arms that are actually effectively in the off position. So this works great if you're looking for a very inexpensive high power solution with very low loss. Part of the trouble here is that once the system starts to go down, you tend to get a kind of cascaded catastrophic failure. So a lot of our military customers really don't like this sort of configuration. This tends to be limited to more of our commercial sorts of customers. These can be built over fairly significant bandwidths. We've built them with as much as a 3-to-1 bandwidth, 2 to 6 gigahertz sorts of bandwidths here, depending on the actual application. But they're extremely efficient. So, and in some customers, if efficiency is very high on your priority list, this very well could be a good solution for you.
Okay, and you have at different times talked about combiner divider networks. Can you explain a little bit about that?
Sure. So this is another great thing that we need to consider also is that 90-degree hybrids can be used very effectively as power combiners, especially if you're using a non-coherent sort of power combining. In this case over here, if you're non-coherent, you're going to lose 3 dB worth of insertion loss. A 90-degree hybrid is a very cost-effective way of building something that can combine, two signals and port that excess energy out to a termination. It's a fantastic way of doing it. Conversely, if you use two 90-degree hybrids, one is a dividing hybrid, and then have your amplifying stage, and then have a second hybrid as your combining network. It turns out that if you offset the phase of the hybrids by the 9 degrees by the initial dividing network, and then recombine them with an inverse network with the same phase offset, you get a very efficient power combining combination here. Power combiners do not necessarily always have to be in-phase power combiners to get highly efficient networks. This takes advantage of several things. First of all, a 90-degree hybrid typically have a very low insertion loss because of the shorter path length inside of them. And because these networks are reciprocals of each other, or mirror images of each other, there is a lot of self-correction that happens for amplitude balance and phase errors within each of the hybrid networks. As a result, you can build extremely efficient networks if you want to take a single signal, split it out, run it through a multiple amplifier stages, and then recombine it at the output. It's a fantastic way of doing this, and we've been quite successful doing this. And when we do this, we do sell these as a matched set of a divider and a combiner network.
Wow. Well, it makes me wonder, how does TRM decide which configuration is the best fit for each customer, or how do you modify or customize the different configurations?
Well, Paul, I think that really comes into our TRM differentiators. Since there are so many different configurations that are possible for these sorts of things, we want to go in there. That's why we really want to go in there, talk to the customer, find out really what it is they're trying to do, find out all we can about their application, and go through there and then work up between the various solutions to figure out which one's the best ones to fit their needs. Sometimes customers are very interested in bandwidth. Some people are very interested in making sure that the system is bulletproof. And on other times, they're looking at power combining efficiencies. All these sorts of things lead you to different technologies, and really we need to understand what it is they're trying to do in detail to help them make the best decision as far as to which way that we go through there. And this is what we like to do. We like to work with our customers to find out really what is the best approach, because TRM can build a multitude of different approaches to really virtually any product. And we want to make sure that what we're going to actually end up with really will be the best fit for the customer and the best thing for our customer's customer.
Okay, and what about screening and validation? Is that part of the process?
Absolutely. If that's part of what we like to do as far as to how we like to work with our customers. If a customer will like to have a part and they like to have some custom screening, we're happy to do it for them. It makes their confidence level when they deliver their product to their end customer that they're getting the product that they really need.
Okay, and you've oftentimes spoken about the importance of packaging. Can you explain a little bit more about that?
Absolutely. So what we do here is not only just the circuit, what's important really with our customers, and this goes back also to the different approaches of how we do this. The package that this goes into, it has to meet and fit into the customer's network. If that means taking some connectors and changing the location of how that is, a mounting surface, or whatever it is that they need to do, whether it's a size requirement or whatever else. TRM very much likes to work with our customers to go through there and actually really customize these parts so the customer gets a part that fits like a glove really up into the next application.
Wow, lots of good information again here, Shaun. Maybe we can wind this up with a bit of a summary.
Sure. Basically, power combiners are you think about them as being reciprocals of a power divider. But in reality, it's all about being careful, understanding the signals, and watch where is the power, where's the heat going to go. So as a result, we have to be very careful when we design power combiners to understand where the energy is coming from and where it's going to go. So very often to think about especially it's one of my first question always is this a coherent signal coming in or a non-coherent signal coming in? That kind of branches us off into the sorts of technologies and sorts of power handling understanding that we need to do. I think also is keep in mind here is that, you know, an in-phase power combiner may not be the best solution. Maybe a 90-degree hybrid will work if we're talking about combining two CDMA radios, for example. Well, you'll never have an in-phase combining event. Why tie your hands to an in-phase combiner if it's not going to add any additional value? And again, think about the topologies of what we're doing here and understand the bandwidth. A lot of topologies are great for handling high power. They just don't have a lot of bandwidth. And really understanding those sorts of trade-offs. Something else also is don't always think that a combiner is going to be combining hundreds of watts. Very often combiners are inside the radio back at the low power stage, and we're combining 100 milliwatts. At those sorts of levels, certainly you could probably just take a standard power divider and turn it around and use it as a power combiner.
Well, you know, as we've said before, I know technically TRM sells hardware components, but I'm hearing the relevance and the importance and the passion associated with solving problems or sharing innovative ideas to customer programs to make them work. So on the screen, you can all see our hotline number, our engineering hotline. We would welcome any questions that you might have. After our last tutorial, quite a few people got back in touch, and we're happy to provide whatever information we can. Shaun, thank you so much for your time.
Yeah, thank you, Paul.